Lee, assistant professor here at the School of Information and Library Science at the University of North Carolina, and I'm here to talk to you today about digital preservation, which is an area of increasing importance and concern in the contemporary world. To give you a bit of an idea about what I'll be addressing today, I'll be talking about the issues of preserving meaningful information, some of the aspects of digital objects as things that we tend to preserve. Even that term digital object is somewhat deceptive, but that's how we tend to think of these things. Some issues associated with layering and abstraction, the fact that digital objects depend on a variety of layers of technology. The fundamental issue that technological obsolescence is part of this game, which makes it impossible to depend on one platform for very long. Some of the technical strategies and this notion of significant properties, the idea that we want to figure out what aspects of the digital objects we want to preserve over time, and just a few general conclusions. So as an origin to this problem, documentation of activities in general allows us to, as David Levy would say, throw our voice, right? We're able to convey something about the world that we've experienced to someone else who hasn't experienced it. We can document parts of our life. We can engage in correspondence with people at a distance. Historically, contributions have been through oral communication and then physically fixed artifacts, right? Documents, photographs, and increasingly things in digital form. One of the problems in this kind of situation is that all conveyance of memory, even to ourselves, even rehearsing a memory from something that happened to us in the past, runs into this hermeneutic gap, the fact that we don't always have a perfect matching of understanding between what happened and what we're conveying now. The context is never completely captured or perpetuated completely. As curators, as archivists, as librarians, professionals have to make decisions about what aspects they're going to carry over time. So we use our current understanding and our place in the world to fill in gaps. Right? If you look back at a transcript of a conversation, you come to realize there's a great deal about the context in which it took place that allow people to convey that meaning from one person to the other. This is one of our greatest strengths as humans. We're very good at filling in gaps, understanding nuances, recognizing patterns, making inferences. But as we'll talk about, this makes it very challenging when we're explicitly codifying things in information systems to convey memories over time, because we don't always have all that supplemental information to fill in the gaps. So archivists and other record keepers, people who have tried to retain information over time, have tried to fill in these gaps, address this issue in a variety of ways. One is adding what we generally call metadata, some kind of descriptive information, a filing cabinet around a document so you don't just look at the document. Policies at the point of creation, things like naming, filing, different genre conventions. If you filled out a form that I'm familiar with, I already know a lot about how to interpret it because it fits a certain genre. Archivists have engaged in appraisal, the determination of what's worth preserving over time, the idea that we're taking a sliver of a sliver, as Vern Harris would say, of the documentary universe and making decisions for the future about what might be most relevant to them. Retention scheduling, which complements that, making decisions about particular things, right? Maybe I'll get rid of some administrative forms, but I better keep my birth certificate around for quite a while. Disposition actions, which is to actually carry out destruction of materials and transfer of them. If 95% of what I have is kind of distracting, if I get rid of it, it makes it easier for me to keep track of and understand the information that I do retain. Transfer of custody to trusted third parties. So if I put something in here at the University of North Carolina in the Wilson Library, I trust the professionals there to ensure that they will provide interpretation of it, they will keep some of its characteristics over time, they'll associate it with other documentary information that allows people to understand it. And a great deal of labor-intensive arrangement and description, creating finding aids, creating catalog records, creating all kinds of inventories and indexes that require a great deal of time and effort and intellectual energy that can have a lot of payoff but become somewhat problematic in a digital environment in which the volume is so large. Controlled custody environments, so ensuring, for example, that if somebody attached a document to another document, if I come back 20 years and look at it, I'll still understand that association because someone hasn't walked in and tinkered with it and pulled the document out. And one-on-one reference services, right? A great deal of helping people fill in the gaps is, who is this person in this photograph? What would these meeting minutes have been associated with, right? Giving people an understanding of the documentary universities we're a part of, generally through professional practice that ensures that some of that contextual information is still there. an aphorism that I find very useful in this environment, in all documentary issues, but particularly with digital preservation, is that resources are limited and meaning is expensive. If you think of those gaps about trying to fill in the contextual information, about giving people a better understanding of something they didn't directly experience, it's very expensive. You provide additional descriptive information, you supplement it with other documents, you give them a lot of explanation, you put layers of meaning on top of it. You can't do that with everything. And in a digital environment associated with that concern are two often competing demands. One is more heterogeneous access, right? The idea that regardless of what kind of little device I'm holding or where I am, whether I'm at work or at home, I want to be able to access the information that is interesting to me. So that means there has to be a great deal of affordance for different kinds of architectures to run on top of. And the other is more functionality. I don't just want the thing to run anywhere, I also want to be able to query it and sort it and manipulate it and do a variety of things. If you combine those two things with some of the issues I'm about to talk about associated with obsolescence, you realize that we have to make this resources are limited kind of decision. We have to decide what we're going to retain, because this requires a lot of different systems that need to be supported, and the second point requires a lot of depth in terms of all the functionality that needs to be preserved. And it's very unlikely that all of those things can be done at the same time in a changing technical landscape. So some of the underlying issues are, we're talking about bits here, right? When we're talking about digital objects, things residing on some sort of physical medium as what we call a 1 or a 0. Right? An electrical engineer will explain to you that even what we interpret to be a 1 or a 0 is subject to a lot of interpretation by the equipment. It has to know what stands as a 1 or a 0. So how do we address some of these things? One is to be stored in appropriate environmental conditions. We can carry over a lot of knowledge we have about paper conservation and other kinds of physical materials, photographs, generally keeping humidity low, keeping temperature low, trying to keep the variance of temperature and humidity low. You know, don't put big magnets next to your hard drive, right? Take care in handling of media with optical media in particular. One of the most likely ways to lose bits is that somebody scratches it or mishandles it. Maintaining the integrity of the bit stream through security, making sure someone hasn't changed it unknowingly. Checksums in various ways that create calculations to ensure that if a 1 or a 0 has been flipped, you know that that's happened and you can fix it. Periodic sampling and other validation. If you're running a big data center and you have all kinds of files sitting on media on shelves, you need to pull them periodically to see whether basically you've been experiencing bit rot, the bits have been disappearing. So two main things, one being bit rot, which is if you write something to a magnetic medium, which is just a bunch of charges, you know, on some magnetic particles, they will lose their charge over time. Eventually, if you put a floppy disk in a drawer and you pull it back out, you won't be able to read all of the bits because they won't be there anymore. The other is that the density and speed of the storage media keep increasing at such a dramatic rate that it makes a great deal of economic sense to move off of that old medium, right? If you need to store a gigabyte, you don't start adding up a whole bunch of 1 megabyte floppy disks, you put it onto a new medium. Those two things mean that part of preserving something over time doesn't mean the kind of fixity you have in a physical environment. It means periodically refreshing it to a new physical medium. And ensuring the integrity of the bit stream in such transfers is extremely important. The idea that I've moved it from a floppy disk to a CD, from one hard drive to another, that I know that in that transfer, what I care about in terms of the bits is still there, because those are the cases in which there's likely to be some kind of problem. I hinted in the beginning that the very idea of a digital object is somewhat of a anachronism. It's really a way of us to think about dealing with the physical reality that we're used to in a digital environment, because digital objects are useless and arguably don't even really exist as a digital object if no one can interact with them. A digital object is a whole bunch of instructions for future interactions. That's what they are. They're little bits of code that know how to interpret the bits. They're the bits themselves. And so there's very little notion in a digital environment, in the same way that if you had microfilm and you could zoom in closely enough, there's always going to be a shape there. If you don't have the apparatus around a digital object to recreate the interactions with it, you don't really have a digital object. And only a small portion of the digital preservation work is actually treating them like physical artifacts. Some of those things about environmental controls, ensuring that somebody doesn't come in with a big magnet, that you minimize the dust, right? There are things you can do to treat them as physical artifacts. But the majority of the hard work of keeping things meaningful is at higher levels of abstraction, of ensuring that they can be interpreted, that there are formats that can be read. Jeff Rothenberg takes a very extreme position, basically contending that all digital objects should be seen as programs, in the sense that if you think of the most simple case that people tend to lay out, it's ASCII text, right? Very simple, plain text. We think of that as a bunch of A's and B's and C's and D's. It's actually a set of ones and zeros that basically has to be run effectively through an interpreter that tells you that 10010 is an A, and then allows you to read it. In the same way, in many ways, that if you had a program to be run, it would have to be run through an interpreter. If you had a Perl script, it wouldn't be very useful to you unless you had the software that knows how to apply that script. So a very powerful concept in computer science is this notion of abstraction. And Phil Agre summarizes this very nicely by basically saying that computer science develops by building abstractions on top of abstractions. And part of the important point he makes is that this is technical work, but it's also social work, in the sense that it divides up whose realm of responsibility lies where. I can abstract out the details of the underlying hard drive and just deal with the operating system, or I can just deal with a layer above that. It's a very powerful notion for dealing with complexity, and it's also a very important notion when thinking about digital preservation, because we hope to the extent possible to abstract away from the details of the underlying hardware and software the characteristics that we really care about. If I can say this digital object is the same digital object regardless of whether it's running in Linux on an Intel processor or some other processor, you gain quite a bit. And collaboration will be required, and it's a very important thing to recognize when feeling very constrained and stultified by your lack of knowledge in the technical world, to recognize nobody has full expertise of everything in this arena, right? Everybody in the world of information technology has to recognize that they collaborate with people who have expertise on elements of the architecture that they don't fully understand. So if we work through some of these layers, if we go through this scenario basically of someone, say, who's a manuscript curator who goes into the attic of someone who has just reached the end of their career, say they've retired, they're donating a bunch of materials from their attic, and you find in a box a disk of some sort that is 40 years old, right? How do you actually interpret that? How do you actually determine what is sitting on that? There's the physical medium itself. You need to read it. Let's say, for example, it's a CD. You have the actual disk, right? You have to know how to read that off of that with a laser. You have to recognize the pits and lands, the holes and the gaps between the holes. You have to recognize what counts as a bit. Is it a certain charge? Is it a certain size of hole? Things that we take for granted when everything's running effectively, but if you have to deal with some physical medium that you haven't dealt with before, then if you start adding up the bits, you have this issue that if you're able to read off the string of bits and you have something like this, where is the dividing line? Where do I actually cut off into chunks, which traditionally we have tended to deal with as bytes, right? These sort of 8-bit chunks. How do I actually divide this up so that I can recognize this is a definable unit within this big string of bits? We have things like character encoding. I had mentioned ASCII. There are various other ways to encode characters. Just because I have ones and zeros doesn't mean I actually know what they stand for. We need to understand the instruction set architecture if it needs to actually run something that runs on a processor. The physical organization of the bytes, it could very well be that they sit in different places on this medium and you have to figure out some file allocation table that tells you where they are on the physical medium. The logical organization of the chunks themselves, meaning that they might be broken up in some particular file system in a relational database. Then you need the reading hardware, the input-output hardware, the input-output software, where you have to have a way of actually hooking this up to a contemporary computer and pulling all the bits off of it in a way that can actually be read, right? Once again, this is pretty hidden to us in the contemporary world in which you're dealing with modern equipment. Thank goodness you have a USB port, you hook it up and everything runs just fine. That has a lot of dependencies built into it that won't be there in the future. And then a whole lot of other things going on. One is the operating system itself, which we can break up into various layers. You need the kernel that allows, say, an application that needs to run to actually make calls to the underlying hardware. Various aspects of operating over a network, if you have to pull things off of the network. The windowing environment, if you had to interact in a way, you actually have to click on something. Then these syntax, structure, semantics, content, and values, if you think of data that you now have and you're trying to figure out how to interpret it. Let's say we get from these ones and zeros to something that we now know within ASCII stands for a 5. What does that get you, right? What exactly is that? Is that a floating point number? Is that part of a date? What does it actually stand for? And so the syntax will tell you how to interpret, say, a comma or an open quote or something that actually tells you the divisions between data elements. The data structure will tell you, here are the allowable values, right? You can have in an email header a subject and a to and a from, and if you see to and then something else, here's what to expect. The semantics in terms of how to interpret it, say it's a bunch of data and it's a floating point number, you might have an application that knows how to interpret that specifically. Things about data content and values, meaning what are the allowable types of values that you can put in? Is this a big database of names so that I can always expect last name, comma, first name, and if I don't see that, it probably means the data are corrupt. Data values, meaning very specific allowable values. If it's a state, it could be that there are only 50 potential values. Then contextual linking within and between objects, right? This can be very important, for example, in the case of email. If I have an attachment to email, it's very important that the association between those get retained. If I have an image that appears within a website, I don't just want an HTML file and an image. I want someone to understand that those actually overlaid each other and were part of what, in a page of a book, would be sitting there all on the same page with you. And then potentially various aspects of the user interface. We often think of these things as completely removed from what we're preserving, but if you think of something like a web page and you're trying to give somebody a sense of what somebody would have seen, what was really being conveyed with something, it could be very important for people to understand how Windows put things in front of them, how that particular browser actually operated. And translations across layers are very important to recognize in that, you know, you're a user, you're somebody who interacts with a digital object. You basically, you read, you write, you print, you click, right? You interact with things in a fairly physical kind of way. Programmers tend to write and reuse source code, right? They read these instructions that actually don't make any sense to the hardware itself, but they make sense to programmers because then it goes through these layers to get translated into ones and zeros. And then the physical equipment itself has to deal with these actual physical holes and charges and various things like that, right? Something gets sent over a network, it's a bunch of sounds or flashes of light, it actually has to get interpreted somehow as information. So entering this whole scene is the issue of obsolescence, right? All of these layers work together very nicely if you go out and you buy a computer at your favorite computer store, because it's all been sort of loaded together to run as an operating system together, which is wonderful, and it's terrific that most people don't have to care about these things at a point in time. I really like this quote from Nick Montfort that those who forget the past are condemned to reload it. The idea that if we neglect to be aware of all these dependencies, we're going to be smacked in the face in this kind of scenario where you get a CD that's been sitting in a box for 40 years and you have no idea what the dependencies even are. All the layers undergo change over time, whether it's the operating system, whether it's the hardware, because they're constantly advancing, they're getting faster, they're building more functionality into them. The reference model for an open archivable information system, which is a standard that's been getting a lot of attention in the world of digital preservation, has this definition of long-term. And a very important thing to recognize for this is that it's not laid out as a specific number of years. We're not saying that long-term is 100 years, long-term is 1,000 years. Long-term is long enough for you to have to care about changes in the technology or changes in the underlying user requirements, basically. And the very stark reality of this is that in a digital environment, with formats changing so often, applications being introduced, long-term could very well be 5 to 6 years. It's not necessarily 50 years out. So some of the risks associated with obsolescence are vendor lock-in, the idea that really the way the whole information economy, whether it's content, whether it's software, when it's being sold and provided as a product or a service at a large scale, it tends to depend to a large degree on lock-in, right? A vendor will sell you software hoping that you actually get so much value out of it and you come to depend on it so much that it's very difficult to switch. It's hard to switch from an Office suite. It's very hard to switch from an operating system. And so once you've been locked into a particular part of the underlying architecture, it makes it much more challenging to move out of it in order to put your thing somewhere else, right? Think of all these file sharing environments where people put video and photographs and things like that. There are a lot of lock-in issues there if they suddenly wanted to move their whole photo album out and store it somewhere else. There's this issue of legacy data, which Brody and Stonebreaker had a book back in 1995 called Migrating Legacy Systems, where they define a legacy system as basically any system that resists change or manipulation. So anytime you want to be able to do something new with data, and it makes it very challenging because it's basically an old system sitting around. You know, all these classic cases that people tend to hear about in terms of air traffic control or environments where it simply has to keep running very, very effectively, so you don't have the option of just turning it off and putting a whole new system in place. This can be a real challenge when that legacy system is no longer meeting your needs, but you have to keep aspects of it in place in order to read the information that's useful to you. And the need for digital archaeology, which is a term that Seamus Ross and some of his colleagues have introduced to talk about this idea of having to go back and make inferences about what the heck is actually sitting on a physical medium, right? It ends up being very much like forensics, where you're trying to figure out what is sitting here, what am I looking at? Is this a bit, is this a byte? Am I looking at a database or a file? Am I looking at just a system file that I shouldn't even be paying attention to because it's in no way useful to me? So some of the approaches to preserving these layers of meaning, one is make information useful. This doesn't really sound like a technical strategy, but it's one of the most important strategies for dealing with digital preservation, which is if people find it meaningful enough to invest resources into accessing it over time, they will try to find solutions. If people keep using data so that they put it onto a new medium, it's going to get rewritten in a way that doesn't end up with a lot of the risks associated with putting something on a shelf and coming back to it in 30 years, right? So making the case for information, creating spaces in which it can be constantly reused is a very important part of doing this. Another is policies and procedures, making it very explicit that you have to take certain approaches in order to ensure that digital objects are retained over time, that if a system gets updated, that certain data and metadata have to come along with it. Record keepers' awareness of the issues, so this is both people creating information, people receiving it, whether you're somebody who has email messages that should be retained, raising awareness among those out in this very distributed environment, which we do not have and we're very unlikely to ever have one centralized repository where all these things are being preserved. Making people aware when they put their whole photo album up into some commercial service that there might be some risks associated with it. What format is it in? Is it possible for me to export it? System development, so really trying to integrate into new systems ways of ensuring that they're not so dependent on one particular approach. Supporting standards. System administration, setting up systems in certain ways so that they actually do address some of these characteristics. And then ongoing maintenance. Copying, converting, reformatting, and some things I'm about to talk about, emulating and migrating or normalizing, actually either changing the data themselves or changing something about the environment that they're sitting in that imitates one that you no longer support. So in this environment, there's no such thing as benign neglect. Basically, if you don't play with it, it will break, right? If you simply set something on a shelf in a way that we feel often comfortable with in a physical conservation environment, in which do no harm has become a very important principle of preservation and conservation, that if you're worried about some new encapsulation technique that might destroy the paper, step back, wait, and apply it when you feel more confident. That can be a real challenge in a digital environment where if you don't act very soon, you're very likely to lose the information. So ongoing effort has to be assumed. There are very few viable approaches that involve sitting back for years and years not paying attention to what's in your collections. And the goal is really to minimize work and maximize the benefits. There's no way to eliminate the work entirely. There's no magic solution for putting something in a box and moving on with your life. So there's the traditional dichotomy between different digital preservation strategies has been between emulation and what's called migration, transformation, transformative migration. Emulation is basically use of software to imitate an old system. And it's very hard to talk about emulation without pretending that digital objects are people, and to basically say that they're tricking the files and applications into thinking that they're still running in the original environment. Right? If I have some file or game or application that I ran in the Commodore 64, I can run an emulation environment that allows me to run it on my PC so that basically that application has no idea it's not still running in Commodore 64. Transformation and migration is making changes to the digital objects in terms of switching bits around, changing the way they're encoded, so that they can actually be run directly in a newer environment. Advocates of emulation tend to contend that it better supports these notions of the original as it had its original characteristics and its look and feel. And that it potentially can be more cost-effective than repeated transformations of digital objects. You can arguably get much more economy of scale if you emulate the underlying platform in which dozens and dozens of different applications and formats are run, because you don't have to deal with all of those individual applications and formats. So if we look to the Oxford English Dictionary for a definition of emulation, it's to produce the action of or behave like a different type of computer with the aid of hardware or software design, or to run a computer, a program written for another type of computer by these means. So a very brief history of some of this. This is not a new notion. The idea of emulation really was introduced by IBM with System 360 back in the mid-60s. The idea of using it at a large scale specifically for archives and digital preservation is a much newer introduction. But it's worth pointing out that this very notion of imitating other systems within systems is very long-standing. In terms of operating systems, there have been a lot of efforts over the past few decades to create virtual machines or instantiations of existing computers within computers. It's very common now to run servers within operating systems so that you can have multiple servers running within the same computer. In the development of processors, Intel has supported backward compatibility so that I can run new programs, I can buy a new computer and still run old programs that were designed for one of their older processors by basically using emulation within their processors. It's also very important in designing new processors to be able to do emulation, because before you've fabricated the physical processor, you have to have some way of imitating its functionality to ensure that your design is sound. I had mentioned virtual machines. Java has been the most widespread and popular one, starting in the mid-90s when the web was really taking off. The notion of having an application run on top of a virtual machine that imitated this imaginary computer so that you didn't have to write a program that could run in dozens of different environments. As long as every one of those individual environments could imitate this virtual machine, they could all run within it, and you'd end up getting a sort of an n plus n as opposed to n times n situation. Terminal emulators, many are familiar with the idea of basically logging into a system where you look like you're dealing with an old mainframe, which is actually imitating that environment within your contemporary applications, within your contemporary computer environment. And lots of games are supported through emulation, and it's worth pointing out that this trajectory of obsolescence isn't just linear and absolute. People don't just give up on an application and move on. People become enthusiasts for old applications and old environments, and a lot of them have relied on things like getting a ROM image, an image of what was originally stored, and then emulating the original hardware so that, for example, I can run an old arcade game on my new computer, right? And so there are aspects of that that we can take advantage of when thinking about emulation for digital preservation more generally. Some of the open issues related to emulation: what level to emulate? Do we really want to imitate things about the application that something ran in, or do we want to go all the way down to the instruction set architecture? So I'm basically emulating something like the Intel processor. You can gain a lot more by trying to emulate at a very, very low level, so that really you're treating everything on top of it. If I'm running Microsoft Word, if I'm running all these things, I'll just treat those like a digital object like anything else. And as long as I can continue to imitate that old computer and all of its equipment, then I don't have to worry about as many of these dependencies. Another is when to create the emulator. Do you basically generate an emulator of the environment at the time that it's available, or do you try to create an emulator specification that will allow you to do more of that into the future? How to develop emulators, for example, what language. There's been some very interesting work in the UK on a language called C++. The idea of basically a programming language that's simplified in order to be the platform that would be used to create emulators, so that when we know that languages are going to change over time, it'll be easier to move from that source code to some other source code in order to keep that emulator going. And intellectual property rights. There are a lot of issues embedded in all of this about what you have permission to copy. If I could emulate the original hardware, but one of the vendors who sells me the software that runs on that hardware isn't going to allow me to run it through that emulation environment, then I run into issues about what I'm likely to be able to actually run into the future. Dave Holdsworth and Paul Wheatley have this graphic way of representing the fact that even when you do emulation, you still have technological obsolescence issues, because the platform that your emulator is running on is going to change, right? Now I have this emulator that's running on, a Pentium 2 or whatever it happens to be, that is on your old computer running in your office, right? And then you move to the new environment that has some new instruction set. Well, now you need a new emulator. So basically, you try to keep the same preserved digital objects, but then you make incremental changes to the emulation environment in order to accommodate for changes in the underlying host platform. Transformative migration at the other end of the spectrum is really about changing the bits and bytes to run directly on newer platforms. This is one that a lot of people have direct experience with, in that if you open a file that you created in some old version of a word processor, for example, it will often do something either transparently or semi-transparently in the background to change it to be run in the new application. It's also very widely used to manage legacy systems. As I had mentioned, if you're in a mission-critical system in which you have to make incremental changes because you don't have the option of just turning it off and putting a new system in place, you have to constantly be dealing with these ways of changing the bits and bytes in order to get them to run in the new system. It can be very expensive, and it can introduce errors of translation. This is often characterized as the telephone game problem, right? You have a circle of 20 people and they pass a message around. By the time it gets to the end, the message is completely different. Well, that's because you don't have a conversation from the first person in the line to the very last person on the line. Each time someone speaks to somebody, you can have errors in translation. So some of the ways to think about addressing this involve aspects of migration on request, the idea of making the transformation from some original digital object, from some original bit stream, into what Jeff Rothenberg has called the vernacular copy, the vernacular version, at the time that it's needed, right? Because then at least you only have one generation of migration. You don't have change to change to change. And layers of technology can be minimized, which is certainly one of the advantages. When you start thinking about layers of imitation of underlying platforms, sometimes the situation gets a bit more complex. But I'll point out again that these are a dichotomy laid out in order to give contrast between different approaches, but a lot of viable digital preservation strategies have some aspects of both, right? If you do something as simple as retaining a script to be run within a database, for example, you're doing aspects of keeping the application around. You're trying to do aspects of imitating the original environment. Some things to point out as common considerations across these strategies. One is that they all use standards in some way. The idea that I will support XML, that I'll put something in an open standard that other people can understand so they can run applications that also understand it, is important no matter what strategy is adopted. Even if, for example, you are an advocate for a very pure form of emulation where you're just trying to imitate the original environment, there are still aspects of the documentation, various different descriptive information, the emulator specification itself that has to comply with some kind of standard. There's a general consensus, I would say, among those in the digital preservation community about keeping the original bits. The idea of whatever you end up doing with it over time, you want the original bits to be in place so that you can potentially do this one-off migration where you create a derivative copy directly, And you can also do a lot of quality checks because you know what the original bits were supposed to be. If you end up with all of these changes over time, you can't go back. Dave Holdsworth, who was co-author of that piece on emulation that I mentioned earlier, likes to give the example of ASCII to EBCDIC to Unicode. So EBCDIC was this variant on character encoding, right? Not ASCII, but a different way to represent bits. If you had moved from an old legacy system represented in EBCDIC into ASCII, there were certain control codes and various characters that you lost. If you now move into an environment where you have Unicode, which is a new way of encoding characters that's much more inclusive, you could get back some of those codes from the EBCDIC that you had lost if you had gone from EBCDIC to ASCII into Unicode, right? So the notion there being, aside from all these acronyms I've just thrown out, that if you had retained the original EBCDIC, even if you decided that you no longer wanted to use that second generation technology, you could pull out some of the characteristics that would have been lost within the new generation of technology. So there's something to be said for keeping the original bits. Transformation can be minor or extensive. There can be migration, for example, that's basically completely reverse engineering. You recreate everything about the application that was run within it. And that both transformation and emulation can take place at various points throughout the process. You can try to do transformation prospectively, you can try to create emulation environments prospectively, or you can deal with them much more at the time needed, depending on what people's use environments are at the time. So in order to inform all of this decision making about what seem like pretty high-level complex strategies is this notion of significant properties. From the CEDARS project, that whoever takes the decision that a particular digital object should be preserved will have to decide what properties are to be regarded as significant. And the Chameleon project and a variety of others have taken up this notion of significant properties to think about what kinds of digital preservation strategies should be adopted. The notion being, again, if you think back to a digital object as simply a set of instructions for potential future interactions, right? It's not just like if you look with a microscope closely enough on a hard drive, you'll see the document sitting there. What you do is store a whole bunch of instructions for potential future interactions. You have to decide what about those future interactions has to be retained in order for this digital object to be authentic, to be useful. Is it something about some embedded codes? Do you need the comments with an HTML file, or is it okay if you just see what text appeared on the screen? Do you need to know something about what was within a spreadsheet? Do you need to have line breaks, font, right? You can think of these various characteristics that might need to be retained. And they can really help to inform these decisions about what preservation strategy to adopt. It can involve writing specific provisions into a submission agreement. So I say, I trust you to take my materials as long as I ensure that this checksum that I applied gets carried forward, as long as I'm an artist and the color rendering has to appear a very particular way, or I don't think it's the same piece of art anymore, right? Those things can be specified at the time that things are transferred into a repository. Also developing criteria and empirical tools for evaluating them. If you wanted to apply a variety of methods from human-computer interaction to these problems and say what differences will actually help support particular research tasks, what will help people better understand historical materials, what will help lawyers and judges ensure that something stands as evidence, you can get very concrete about what those properties are that they might actually need to retain. And then documentation of preservation decisions over time. Things will get lost, decisions will be made that certain things are just too expensive or too complicated or not worth preserving. By specifying in terms of these significant properties what you're doing, you're potentially gaining trust of those who are giving you the responsibility of managing these materials by letting them know what you've actually decided. These are things I'm simply not going to retain. They're too complicated, they're too difficult, they're not worth the resources. So if we think of this as cost-benefit analysis, there are the costs, which is, quite straightforwardly what you have to put into it in terms of resources. The benefits are all of the either direct or indirect values that people get from the existence of these things over time. Either I use them myself, or say, someone acting on my behalf uses them. A journalist looks at those materials and then writes an article that informs me. And the opportunity costs are the failures to derive those benefits because you choose some different approach, right? I made that decision to move from this EBCDIC encoded data into Unicode, and I knew I was going to lose a few control characters here and there. That was an opportunity cost, but it also meant I realized I didn't have to invest a lot of these resources that I would have otherwise. So it's impossible to directly measure now what the value might be of future use. So one possibility is to actually do user testing, to actually do ways of deriving data so that we can try to make guesses about what differences make a difference, right? What differences actually matter to people. If we think about the functions and activities we want people to engage in, we should think about what are the characteristics that actually matter to people trying to engage in those. And the hope is certainly to preserve as many properties to support as many uses as we can, but the reality is that most institutions are preserving things for particular populations. Within the OAS reference model, this is called the designated community. These are the people you're really trying to serve. If their terminology changes, if the software they're using to read the materials changes, you really have to make changes to accommodate them. And each one of those decisions can carry with it resource commitments. So there's no single solution. It really involves making decisions about what attributes should be preserved and which differences matter. You know, does color matter in this case? Does font even matter? If I'm looking at an email message from you and I'm aware that it could have been represented in 25 different ways in different email clients, does it really matter that you know how it would have looked in my version of Thunderbird that I was using at the time, right? In some cases, absolutely. In other cases, that would just be a phenomenal waste of resources to try to do. And make and document educated guesses of the costs and benefits. Part of being a trusted professional in doing this kind of work is conveying in the present and into the future why decisions have been made, what has actually been lost, what didn't get retained, and why. And by keeping the original bits and kind of documenting the activities, you also push it off to the potential users to do some of this work themselves. If they care enough about some characteristic of the original, they might actually go to the trouble to do some of these things themselves. So we must identify both what's desirable and possible, right? Best, most informed guess about how objects will be used. We always make the best guesses we can, and we sometimes get it wrong, but that's what professional activity is really about. Characteristics that support such uses. What are the current technical approaches and techniques that are available? What can cost effectively be preserved? And all these decisions should be well documented and revisited periodically. Rothenberg and Vixen have this way of representing this where basically you've got a top-down and a bottom-up combination of what we really want. What would be the requirements for, say, you're keeping the records of some corporation? What would they really want in the characteristics of their records? And what's technically feasible given what we have at our disposal, right? And neither one of these is completely fixed. If we care enough about it, we can do the work to actually develop software to do certain things. But there's always going to be this trade-off and this iteration between these two things to try to make determinations about what is really viable given what we want to be preserving. Keeping in mind that these issues of social memory, of accountability, of future understanding of the contemporary world is really what we're trying to get at. We're not buried in the bits just to be buried in the bits. We care about retaining these things for some kind of conveyance of meaning over time, and that's what should really convey the decisions. So finally, I would just conclude with, there's this aphorism from the early days of the environmental movement that have really carried through a lot of social movements of thinking globally and acting locally, right? Not getting so constrained and stultified by the fact that this is a challenging world we live in, but being aware of the larger context and acting locally. And I think that it's fundamental in long-term digital preservation to be thinking in the long term, to be aware of that definition of the long term that I gave you, that we can't simply design systems to optimize for the present, but by the same token, we will not come up with a solution for the next 100 years right now. We will come up with incremental solutions, ways of developing systems that are better than others, that lock us in a little bit less, that provide enough contextual meaning that we'll be able to understand systems into the future. And that's the way that we'll actually advance toward the long term. Thank you.